So this is what it has all led up to do. I mean, everything from the very beginning of the semester all the way until this moment that we are sharing together right now, together as one big lovable bunch, just virtually online. This is what it has all led up to do. So in the very beginning of the semester, we talked about this concept of formula weight, right? We said this is what formula weight is. This is how we calculate formula weight. You need to show the work on how to calculate formula weight. And then in the assignment, I gave you a bunch of different formula weight calculations, and I said, show me how you get the money. Show me how you get the number. All right. So that's the first thing that we did. And then we went on and we talked about this idea of going from moles and gram. So the concept of being able to take in a gram amount of substance, converting it into moles. Why? Who knows? I told you that we would figure that out a little bit later, but we at least can convert gram to mole and mole to gram. And we do that by using the formula weight number. Well, moles, we eventually found out, was this common language. And the common language is basically what everything has to be in order to go from a product to a reagent or vice versa. And that's kind of what we led into the third topic, major topic, of balancing chemical equations. We said, well, you got to do this because if you can't do this, you can't do anything else. So we did a whole assignment on balancing chemical equations, looking at what was there, not predicting them, just looking at what was there, putting the coefficients in front and calling it a day. And then we end up doing stoichiometry. All right, so stoichiometry was the idea that we can now, at this point, we have enough information that we can now take a gram of substance, whatever we measure out in the laboratory, and predict how much product that we would end up with that particular starting amount, right? So stoichiometry, we were able to take grams of one thing and go to grams of another thing. Well, in order to do that, you had to have check formula weight, check moles to gram, check balanced chemical equation in order to do this thing that we called stoichiometry. All right. So now this video is going to be very short. It's probably going to be very brief. I hope I can get through just one or two examples and that will kind of convey the point across. It's stuff that we've really already talked about in other videos. This is just a rehash all over again. That's all that this is. And it is going to concern this topic of what we call percent yield and percent error, and maybe this word called theory yield and actual yield being thrown in. Now, again, these words could have showed up in other videos. You might have taken notes on them already, but now we're going to give it kind of its due diligence and we're going to say, listen, you are so important and we want to pay attention to you and we want to make you feel loved and we want to make you feel like you are wanted and we're going to calculate percent yield and percent error because of it. Okay. So how do we do this? Folks, the hard part is already done. It's already finished. You know how to do the individual parts. You just need to piece them together. All right, so let's take a look at an example problem. Suppose that we have this chemical equation, C2H5OH plus 3O2 goes to product side 2CO2 and 3H2O. Oh, well, all right, I see the balanced chemical equation. It's balanced for me already, right? How do I know it's balanced? I didn't even check it. I know because here they're giving me big coefficients out in front. The first one doesn't have a coefficient, but who cares? We know that that's understood to be a 1. So the balanced chemical equation is already taken care of. This is something that I would have to do if it was not balanced for me, right? And that's why balancing chemical equations had its own assignment sheet. It had its own area that we placed a focus on because it is important leading up to the percent yield, theory yield, all the other stuff that follows through. All right, so balanced chemical equation. Check. I've got it. Next up, the question. The question is going to say, there's your equation. These are all of the reactants, and these are all of the products. What if? What if, number one, the question said, let's say that you had 10 grams of C2H5OH. How many grams of oxygen would be needed for the reaction to take place? All right, so this is very similar to the stoichiometry section, right? Nothing new that I'm going to talk about here actually hasn't already been talked about in another video. But it is a revisit. It is a review that's going to lead us up to this thing called theory yield, percent errors, and so forth. All right, so how would we set this problem up? It's not a big deal. I know how to set this problem up. And what I would do is I would take the number, the given 10 grams of C2H5OH over 1. I would take that value. Grams of that stuff on the bottom. It has to go to the bottom on the next step. And I know in order to convert one compound into another, that's what this is all about, right? We've got the C2H5OH stuff, and we need to go to O2 stuff. So in order to do that, I need the common language, and that common language is a mole, and the only way I can go from gram to mole, like we figured out in the previous video, I hope that I learned something, is formula weight. So I need the formula weight of C2H5OH here. I hope that you can calculate that at this point. And the formula weight is going to be 46 grams per 1 mole. You can look that up, Google it, do the work. 2 times 12.01 plus 1.01 times 5 plus 16 plus 1.01. It gives me 46.0. Give or take a little bit, I've rounded it off. If I stop there, though, that is mole of C2H5OH. I don't want that compound. I want something completely different, right? I want O2. So if I'm starting with this much stuff, how much of this ingredient do I need to add in order for the recipe to work? That is what we are trying to figure out here. In order to do that, I need to get into mole. That is the common language. It's the only connector piece that we can use to connect these two things together. So mole of C2H5OH, mole of O2 on top. Well, based on that chemical equation, there's a 1 in front, right? So a 1's going to go here. And based on the chemical equation, there's a 3 in front. And a 3 is going to go there. Nothing's different yet. We've done this same stuff over and over and over. It looks like everything that we've talked about so far. All right, I'll bring in, I'm not quite done because the question says how many grams, not how many moles. Mole of O2 on top, mole of O2 on the bottom, and I need to go to gram of O2. How do I do that? Formula weight. That's how we do it. So 1 mole of O2 has how many grams? Well, 16 plus 16, that's going to be close to 32. Again, I'm going to round it off. So, folks, this is basically how we calculate this thing called a yield. But in this particular case, it's not really a yield because I'm not making it. This is just something that is required. It is an ingredient, an amount that I need because O2 is a reactant. So I'm going to have to mix this amount with that amount of C2H5OH in order for the recipe to work the proper way. Well, if we were focused on the product side of the house, either CO2 or H2O, then I can calculate yield, and I calculate yield the exact same way. So just to give us an idea of the math, just to review that before we go further, I'm going to take 10 grams, and then I'm going to divide it by 46, and I do that because 1's on top. And then in the next step, I'm going to multiply by 3. And then in the next step, I'm going to multiply by 32. And this will give me the number of grams, 20.87. I'm going to round it off to 2 sig figs. All right, so 20.87 grams of O2. Again, this is a reactant. That reactant is an ingredient. I will need 20.8 grams of O2, and I need to mix that with 10 grams of C2H5OH in order for this to work out the right way. That is the recipe. That is what I'm after. Theory yield, percent yields, all of these other terms that we're getting ready to talk about, folks, it's the same thing. There's no difference. Except the difference is we're mostly focused on the products every single time that we do these questions. All right, so for that reason, I'm going to circle the products. And that means if I take this same question that we have been working on now in previous videos, and let's say that I just get rid of the O2, and now I'm going to put in something else, and I'm going to put in, I don't know, CO2. I could do either one. Doesn't matter. As long as it's a product, it's going to work. So we are particularly interested now in a product here. How much product would be formed? That's the difference. I'm not worried about the ingredient side of the house anymore. I'm now worried about how many cakes can I make with it? How many sandwiches can I make with it? What is the product on the product side? What am I going to end up with if I do this the proper way? If everything works out perfectly, how much am I going to end up with? That is what we call theory yield. And that's how these questions are going to be stated. What is the theory yield of CO2 in terms of gram? Because I don't need that anymore. I'm making it. I don't need it. And that is a slight terminology that people feel very uncomfortable with at times for some reason. But that's all that it's saying. Here's the amount that you are starting with of C2H5OH. We are going to assume that you have all of the other ingredients that you need. Every one of them, we're going to assume that. So if I assume that we have everything else that we need in the equation, now how much product am I going to get? When that gets used up, my product stops. All right, so what is the theory yield of CO2? It's the same setup. How many times do I have to say it? 10 grams of C2H5OH over 1, gram on top, gram on bottom. I need to go to mole. 46 grams per mole. That's the formula weight. There's no difference there. Now I'm into mole. Now I can start giving this common language between the two compounds. Mole on top, mole on the bottom. I need to go to the other compound now. The other compound that I'm interested in, well, this time is actually a product, and that product is CO2. And the number in front of that CO2 is a 2, not a 3 that we used before. So a 2 goes there. Now, the question says how many grams of that CO2 would you end up with? All right, so mole of CO2 on top, and mole of CO2 is going to be on the bottom at this point. Well, that means I need to go to gram. I've got mole. How do I go to gram? Formula weight. I need the formula weight of CO2. All right, that's going to be easy to do. I can probably do it in my head, but just in case, I'm going to take carbon, 12.01, and then I'm going to add 2 oxygens, so 16 and 16. That gives me a 44.01 for formula weight, 44.01. All right, so I'm going to erase that, and I'll write 44.01 there. And I do the calculation just like I did before. There's no difference. The only difference is that I am calculating how much product that should be generated from these ingredients of the chemical equation. All right, so I'll bring up my calculator. Again, ignore the ones. So I'm going to take 10, and I'm going to divide that by 46. And then I'm going to now this time multiply that by 2. And then I'm going to multiply by 44.01. I'll hit enter. And that gives me 19.13. So 19.13 grams of CO2 we should end up with. And folks, that is what we call theory yield. That's theory. All right, so the story here is that I'm in the laboratory, I'm mixing these two things together, I've got the right amounts, and then I calculate this idea. This is how many number of cakes I can make with the cake mix that I just prepared. And then the baker's going to go in and they're going to fill the baking pans and they're going to shove them in the oven, a reaction's going to happen, and they take them out of the oven, and then someone's going to look at this and say, wait a minute, you didn't give me 5 pans of cakes, you only gave me 4 pans of cakes. What's the deal? That's what you actually made. Where's the idea? Why didn't you measure these out the appropriate way? Where's all of the loss? And that baker's going to say, well, you see, I was kind of sloppy. I mixed the cake mix. And then part of the cake mix I left in the bowl because I didn't scrape it all out. The other part of the cake mix I lost on the countertop because as I was mixing it, I was pretty sloppy with it. And then I didn't quite measure it out the right way like I should have. And I didn't end up with this many number of cakes that we thought we would end up with. And therefore, I only can give you 4 and not 5. I'm sorry, but this is just the way that it turned out. So that is what we call an actual yield. So the actual yield is what you actually get. I mean, how much more common sense can that be? This is what you have actually obtained in the laboratory. The amount you have when you did it. For real, when you did it. The theory yield is what you should have ended up with. Shoulda, woulda, coulda. That's what that is. I shoulda, woulda, coulda had 19.13 grams of CO2, but when I made this and when I captured that CO2, I didn't get 19.13 grams of CO2, and instead my actual yield might have been like 10.7 grams instead. Well, that's what I actually got, so that is my actual yield. 10.7, I measured that. I was in the lab, there's no calculations here. No calculations to get actual yields. You're going to have to get that number somehow, some form, some fashion in a laboratory. You measure it out. You monitor it. You capture it. You do something. You know this is how much you ended up with. Theory-wise, though, you should have did it better. Shoulda, woulda, coulda. If only I'd known. So I've got a 10.7 for my actual yield, and then I have a 19.13 for the theory yield. All right, so what do we do with these numbers, right? There is a way that I can go through and I can kind of say, listen, you know, I can see basically if you were pretty good with that experiment or not. And the way that we do that is that we calculate this thing called a percent yield. So in order to calculate percent yield, we do it all the time. In order to calculate percent yield, I'm going to take the actual amount that I received in the laboratory and I divide it by the theory that we shoulda, woulda, coulda ended up with. And I'm going to multiply that by a 100. And that's because we want percent. And this is something called percent yield. So if the question says, what is the percent yield of the blah, 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 blah? Well, I'm going to have actual yield. They better give me that in the problem somewhere. Because if they don't give me actual yield, I'm not going to be able to do anything with it, right? I mean, I have to know what they obtained when they actually did the experiment. The theory yield, I will be able to calculate. If they give me the equation, I can balance it, I can convert things into moles, I can relate it to each other without a problem. The theory yield I can calculate using stoichiometry. The actual yield, they better give it. So to calculate this percent yield, I'm going to now take the actual, and in our case in this example, 10.7, divided by the theory, which is 19.13, and I multiply by 100. And this is percent yield. All right, so that seems simple enough, right? It's just two numbers that are divided. So 10.7, and I need to make sure my decimal's there, divided by 19.13. And then I'm going to multiply by 100, because that's what it tells me to do, percentage. And I get 55.93. And that's my percent yield. So what that means is that I made 50% of what I should have ended up with. You can tell that by looking at the number, right? 10 is almost half of 19.13. So my percent yield here is 55%. Could you imagine if you were assigned to make cakes and every time you made cakes, you only ended up with half the amount that you should have been baking the whole time with the batter recipe? Oh, this recipe should make 10 cakes, and you're going to make it, and you're going to do it, and you're going to bake it, and then at the very end, you're going to take them out, and there's only half of what you should have had? Folks, you're going to get fired. Nobody wants a baker like that. That's a lot of waste. In a laboratory environment, we don't want it either. Now, this depends on the process that we do. So if we are doing an organic chemistry process, some kind of synthesis, some kind of refluxing, some type of extraction, something that has a lot of steps that I'm going to have to worry with, organic reactions are notorious to be about 2/3 of what you should be getting. So 66%, folks, here is almost perfect. So 0.66 for my percent yield, but times that by 100, and that will give you 66%. That is really what we strive for in the organic world. Now, there are exceptions. We could go way above, or we could be way below, and that would be acceptable. We know this. Maybe our recipe is just not the greatest recipe ever, and we're going to end up with 3 out of 10 cakes being made, a 30% yield or a 40% yield. And if so, that's fine. There's trends that show that. There's data that shows that. We are not kind of out of line with what the data has been showing, and we'll be pretty good to go. So I need you to keep that in mind. Not every time do we strive for 100% yield. And very often we'll never get it. And sometimes we'll not even be close, and we'll be very, very happy with that. All right. So that's what we call percent yield. Now, the other half of the story is something called percent error. So in order to calculate percent error, this is, well, how many cakes did you lose? How much did you screw up? That's what percent error is. Percent yield is how good you were, right? If I really want you to make you feel good about yourself, I'll talk to you about percent yield. You had 55.9% yield. You did pretty good. At least I can make it sound that way. But percent error is the opposite of. So this is what's left over. So I'm going to take 100 and I'm going to subtract the percent yield from that. That's percent error. That's the easiest way to do it. So in this case, I'm going to take 100. That's what it tells me to do, 100. And I'm going to subtract 55.93. So 55.93. And then I'll hit enter on the calculator. And I get 44.07. So 44.07%. That is error. Percent error. That means I missed 44% of my product. Sometimes that's not very good. Sometimes that will make me get fired if I do it over and over and over and over and over. Nobody wants that. We want to be better than that. I'm losing 44% of what I should be getting? Who on earth would like that kind of thing? And the percent yield is all about how much you got. Good job. You got 55.9% of what you should have been getting this whole time. And then if I want to make you feel bad, but that also means that you lost 44% of what you should have been making. And that's not very good. So what on earth happened during the lab during that time that you did it? That is the difference between percent yield and percent error. All right? So hopefully that will clear up any confusion that you might have when it asks about percent yield, percent error, and theory yield or theory amount, right? All right, so let's kind of do a quick review before I stop the video because we're kind of done already, right? So number one, you got to make sure that you have a balanced chemical equation. Without a balanced chemical equation, nothing's going to work. So you got to double check it every single time. Number two, you're probably going to have to use formula weights of things. So at some point in time, if you're in grams, for sure, you need to convert into mole or mole into gram. And that you need formula weights of these reagents or these products that you are using for that process to go forward. Number three, then you're going to have to use a little bit of stoichiometry. So keep in mind, most of the questions are going to give you gram of one thing, and you need to go to mole of another thing. And then that will give you mole and then back into grams. So this is of one substance and this is of the other substance. You need that connector, and mole to mole is from the balanced chemical equation. So when you do this, this will be your theory yield. That is what this question wants. Theory yield almost every single time. Then step 4, most of the time we know what the actual amount is because we did it already. We divide by the theory and multiply by 100. And that will give us percent yield of our stuff. And then step number 5, sometimes we take 100 minus percent yield. And this will give me a percent error. All right. So what you're going to see on this assignment will be very similar to the stoichiometry assignment. Take this number of grams, convert it into this number of grams of product. And it will be one question after another. Template it the same way. Sometimes these equations will be balanced and sometimes they won't. You're going to have to double check them. You're going to have to make sure that they are or that they're not. Then you'll go through this process of calculating theory yield, and that you kind of already done. And the only extra steps that we're throwing into the picture now is percent yield and percent error at the very end. And that's the difference, and that's why we do them. How good are you? And then how bad are you? That's what it's all about. All right. So good luck with the assignment. It's just, again, a rehash of stoichiometry. I think that if you did that assignment already, you felt good about it, you got a really good grade on it, then go back and take a look at what you did there, because this assignment will be very similar, except it's throwing more of those questions of percent yield and percent error at you. So it's a different little spin, but not a lot. All right. So good luck with the calculation of percent yield, percent error, and theory yield. I think that you'll have a wonderful, fun time. I think that it will go by so fast because you're having so much fun with it that you might ask for another one. I just don't know, but maybe.